All right, let's talk about light. I mean, have you ever really thought about what it is? Most of the time, we just picture it as, these straight lines shooting out from a flashlight or the sun. But honestly, light has this whole secret life, this hidden, wavy side to it that's responsible for some of the most amazing and kind of weird effects we see all around us. So today, we're going to pull back the curtain on that secret world, the world of wave optics. I mean, think about it for a second. Why do soap bubbles have that incredible, shimmering rainbow of colors? You've seen it. Or how can light create these super detailed patterns when it just goes through a tiny little opening? The whole light travels in a straight line idea? Yeah, that just doesn't cut it here. It completely falls apart. To really get what's going on with these everyday wonders, we need a totally new way to think about light. So in physics, we've got two main ways to look at light. First, there's ray optics. And hey, it's great for the simple stuff, right? Like reflections in a mirror or how a magnifying glass works. Super useful, but it's got its limits. Then there's wave optics. This is kind of like the next level up. It says, hey, what if light is actually a wave? And that idea, that single idea, is the master key that unlocks all the really cool phenomena, like the mystery of our colorful soap bubble. And that's exactly what we're diving into today, exploring light's secret life as a wave. And trust me, once you start seeing light this way, it's like a whole new layer of the universe just snaps into focus. Okay, so what is a light wave exactly? Well, the super technical term is a transverse electromagnetic wave. I know, that's a mouthful, but let's break it down. All it really means is that it's a wave of electric and magnetic energy. And these two fields are kind of wiggling or oscillating at right angles to each other and at a right angle to the direction the light is actually moving. Just getting that simple wavy picture in your head is the key to everything else we're about to talk about. All right, now we get to one of the absolute coolest things waves can do. They can interfere with each other. And no, I don't mean like they're getting in each other's way, like two people trying to get through a doorway. In physics, interference is what happens when two or more light waves meet up and overlap in the very same space at the very same time. It's like a cosmic dance. The main rule that governs this whole dance is called the principle of superposition. Now, that sounds super fancy and complicated, but the idea behind it is incredibly simple. It just means that waves add up. That's it. When their high points, their crests, and their low points, their troughs, meet, you just add their heights together. That tells you exactly what the new combined wave looks like. And this super simple idea of just adding waves together leads to two totally wild outcomes. First, when the waves are in phase, meaning their crests and troughs are all lined up perfectly, they basically help each other out. They reinforce each other, making a spot of light that's even brighter. It's like teamwork. We call this constructive interference. But what if they're out of phase? A crest from one wave meets a trough from another? Well, they completely cancel each other out, creating a spot of nothing, darkness. And that's called destructive interference. Now, this isn't just some abstract theory we cooked up. This is real. Back in 1801, a guy named Thomas Young did his famous double-slit experiment and proved it once and for all. He just shined a light through two really narrow slits and looked at the pattern on the other side. And what did he see? A pattern of bright and dark stripes. He realized right away that this pattern of building up and canceling out was the smoking gun. It was undeniable proof that light has to be acting like a wave. So you might be wondering, can we actually predict where those bright spots are going to be? Oh, absolutely. It all boils down to this thing called path difference. And all that is just how much farther one wave has to travel to get to a certain point compared to the other wave. To get a bright spot, that extra distance has to be exactly a whole number of wavelengths. 1, 2, 3, you get it. That's what makes sure they arrive perfectly in sync. Okay, and what about the dark spots? Well, for those, the path difference needs to be an odd multiple of half a wavelength. That little half wavelength difference is what guarantees they arrive perfectly out of step. So the crest of one wave lands right on top of the trough of the other. And poof, they cancel out. Let's make this real with a super quick example. Let's say we've got light with a wavelength of 600 nanometers, and it's creating one of these interference patterns. The question is, what's the path difference we need to get the second bright fringe out from the center? Well, this is where our little formula comes in handy. We just use the one for constructive interference. Since we're looking for the second bright fringe, our n is just the number 2. So the path difference is simply 2 times the wavelength, or 2 times 600 nanometers, which gives us 1200 nanometers. See? Easy as that.
Okay, so that's interference. What happens when different waves meet up and overlap? But what happens when just a single wave runs into an obstacle, or it tries to squeeze through a really tiny opening? You might think it just stops, right? Nope, it actually bends.
And this bending of light around corners or through tiny gaps, that's what we call diffraction. Now, here's the really important part. You only really notice this effect when the size of the opening is super small, around the same size as the wavelength of the light itself. That's why you don't see light bending around, say, a building, but you absolutely see it creating these cool patterns when it goes through a microscopic slit. And you guessed it, just like with interference, this bending creates a predictable pattern. And we've got a formula for it. This whole equation here lets us calculate exactly where the dark spots, the minima, are going to show up, all based on the width of the slit, which we call A, and the wavelength of the light. Let's run through another quick problem. Imagine we have a very narrow slit, just 2 micrometers wide, and we're shining light with a 500 nanometer wavelength through it. The question is, at what angle are we going to find that first dark spot? Okay, so for the first minimum, our n is just 1. We just plug our numbers right into the formula. The sine of the angle is going to be the wavelength divided by the slit width. That works out to 0.25. Then we just take the inverse sine of that, and we get an angle of about 14.5 degrees. Done. All right, so we've seen how light waves can interfere with each other and how they can diffract or bend. But there's one more big secret we need to uncover. And it all goes back to the direction of those little wiggles, those oscillations we talked about at the very beginning. And that secret is polarization. You see, normal, unpolarized light is vibrating in all directions at once, up, down, left, right, everywhere perpendicular to the way it's going. Polarization is basically the act of filtering all those random vibrations down to just a single direction or a single plane. And here's the real aha moment. The fact that we can even do this is the ultimate proof that light is a transverse wave. Here's a great way to think about it. Imagine unpolarized light is like a whole bunch of ropes, all shaking wildly in every direction. Now imagine a polarizer is like a picket fence. What happens? Only the bits of rope that are shaking up and down can actually make it through the vertical slots in the fence, right? Everything else just gets blocked. And the light that makes it through on the other side, that is now polarized light. And we can even calculate how much light gets through a second polarizer using something called Malice's law. So for example, if we take our vertically polarized light and try to pass it through another filter that's tilted at a 60-degree angle, well, the new intensity is going to be the original intensity times the cosine of 60 degrees squared. We know the cosine of 60 is 0.5. Square that and you get 0.25. So only a quarter, just 25% of the light's intensity actually makes it through. So after all this theory and all these formulas, you're probably asking, okay, but why does any of this matter? Well, this isn't just abstract physics for a textbook. This whole invisible dance of light waves is the secret sauce behind some of the most common technologies we use every single day. You know that amazing rainbow shimmer you see on a soap bubble or an oil slick? That's pure interference. The anti-reflective coating on your glasses? It actually uses destructive interference to cancel out annoying reflections. Diffraction? That's how scientists can look at the light from a star millions of miles away and know exactly what it's made of. And polarization? Oh man, that's the magic in your sunglasses that cuts down on glare. It's how the very screen you're watching this on works, and it's the secret behind 3D movies. It's everywhere. So, you see, once you start thinking of light as a wave, all these things that might seem like magic, shimmering bubbles, sunglasses that kill glare, they suddenly just make sense. It's a really powerful change in how you see the world. So the question I want to leave you with is this.